lesson to work through this 2019 paper. And we're going to start with this first question from module 1. So this is an organic chemistry question, right? Okay. So the question reads, the compound CH3 parentheses 2. So this whole compound here reacts with aqueous sodium hydroxide to produce an alcohol, right? So when we look at this structure or the way that it's written there, that condensed formula, we can see that there is a bromine present here, right? So we know that this is a haloalkane, right? So we are concerned with the reaction of a haloalkane with aqueous sodium hydroxide to produce an alcohol, right? So that's what we're concerned with for this question. Okay, so the first part of the question asks us to state the name of the starting compound, which is our haloalkane, specifically a bromoalkane, right? So they're asking us to name that starting compound. So let's just draw this out real quick so we can see our carbons clearly, and then we can apply the IUPAC naming system to get this name, right? So I'm just going to go over here. I'm going to draw my first carbon here that has 2 methyl groups off of it. So there's a CH3 here, and then another CH3 attached to it, right? And then you have a hydrogen there, of course, right? So you have your CH3, you have your carbon, there's a hydrogen there as well, right? So that's that hydrogen. Then we have our carbon, to which we have a bromine attached, right? And then we also have a methyl group attached to that same carbon. So that's our CH3 group. And then, of course, we have this portion over here now, which is just CH, right? Another C, H, and then a CH3, right? All right. So what we're gonna do is we're gonna number the carbons with the one that results in the functional group, or this bromo being on a lower number carbon. So we're gonna pick this side, right? So we pick this side, we have this as our carbon 1 or carbon, put that in a different color. Okay, let me put the number in a red, right? So we label this will be carbon 1, this is carbon 2, this is carbon 3, carbon 4, carbon 5, carbon 6. So that's our longest straight chain region that we're counting. So we just counted 6 carbons, right? And that's indicative of there being a hexane there, right? So that would be the last part of our name, right? And then now we see that the bromine is in which position? It's on the 3rd carbon. So our first part of our name will be 3-bromo, right? Because that's that bromine group. And then the other part of it will be related to these methyl groups that are hanging off of our straight chain, right? So we have a methyl group on the 2nd carbon and a methyl group on the 3rd carbon. So then we'll just write 2, 3, 2, 3, right? It will be dimethyl because there are 2 of them. So it would be 3,2-dimethyl hexane, right? So that's our compound. It's 3-bromo, 2,3-dimethyl hexane. So that's the IUPAC name of this. And as we said earlier, this is a haloalkane, right? So that's our 1 mark and we're good. 1 mark and we're good, okay? Okay. So part 2 now said state the type of reaction which takes place when the compounds or haloalkane or bromoalkane, right, when that reacts with sodium hydroxide. So the type of reaction that takes place, right, when this compound reacts with sodium hydroxide is what we call a nucleophilic substitution, right? So let me just type that in here, that we have a nucleophilic substitution. That's our reaction here, right? So that's for 1 mark. That's all they want, just to state the type of the reaction. Okay. So now we move on to part 3. So I'm just gonna clear all this stuff and move up. So they're saying now outline a mechanism for the reaction using curved arrows to show the movement of electrons. Show clearly the structure of any intermediates formed as well as the final product, right? So, okay, so the first thing we have to do is figure out what are we making? Like, what is the overall reaction? And then we can then break that down into what the mechanism should be. So again, I'm going to just draw out my structure like I did up top. So I had CH3, CH3. There was a hydrogen on it that was connected to another carbon. My bromine was on my 3rd carbon, right? CH3, and then the rest of it is CH2, CH2, right? And then CH3. And that is reacting with sodium hydroxide, right? Aqueous sodium hydroxide. And the net effect or the net reaction is that I'm gonna get a nucleophilic substitution reaction will take place, and now I'll have that this OH group, right, from the sodium hydroxide is gonna come in and substitute out this bromine. So I'll end up getting CH3, CH3. So all we're doing is substituting out that bromine by nucleophilic substitution. So we're gonna put our OH where our bromine was. So that's on that 3rd carbon, right? And then everything else will remain the same. CH2, CH2, CH3. And then, of course, because our bromine then gets replaced by our OH, then the bromine is going to combine with this Na and we'll end up with NaBr. Right? And we know that that's going to be a solid precipitate. So that's solid, right? That we're going to get. And this is going to be aqueous and our alkane. So, yes, to begin with. Okay, so those are our state symbols. So that's what the overall reaction is going to be. So we're going to write out the mechanism now. So the mechanism is nucleophilic substitution. So we're going to write that, and that's as follows. It's a 2-step process, right? So nucleophilic substitution is a 2-step mechanism, right? And so now that we know where we're going or what we're ultimately going to form, we can come up with this mechanism now. So basically what's going to happen is where I'm going to draw my compound again that I have up top. So my starting compound which is the that's the 3-bromo-2,3-dimethylhexane. So I'm just going to draw that back here. See? CH3. Then I have my Br here, right? Because remember, that's what we're starting from. CH2, I have my other CH2, and then CH3. So that's my starting compound now. Remember, the goal is we're going to get to this point where we've substituted out the bromine for the OH, right? So the first thing that's going to happen, right, is that you can see here that this is a polar bond. So there's going to be like a partial positive charge on this carbon and then a partial negative charge on the bromine, because we know that bromine is far more electronegative than the carbon, right? So you have a partial positive on this carbon, a partial negative. So what's going to happen is that the bromine is going to attract the electrons from this bond to itself. And so that's our first step, is that we have that movement of electrons from this bond to the bromine. And so that's our first step, and that's a slow step, which will then translate into this intermediate here, right? So we'll form our intermediate species. Remember, they said that we should show our intermediate. So this is our intermediate now that we're going to form once the bromine has taken all the electrons from the bond to itself. So we're going to end up with CH3, CH3, And now this carbon that the bromine was on is going to end up being getting a positive charge. So that's a carbocation that's being formed, right? And then we have CH3, that's all the same from before. So we'll have our CH2, and then the CH3 that was there before. All right. So remember now that we're reacting this whole thing with sodium hydroxide, right? So there's sodium hydroxide in solution, and that sodium hydroxide supplies these hydroxide ions, right, which are negatively charged, right? And we know that our negatively charged species are known as nucleophiles. They are nuclear loving, so they love positive charges. So what's then gonna happen is that the lone pair of oxygen, one oxygen is gonna be then donated, right, to this carbon, carbocation here. And so that's how we're gonna be able to form a new bond and introduce in that hydroxide or that hydroxyl group, okay? So that's my other step now. This is a fast step. So after the nucleophile comes in and attacks this positive carbon, we're gonna then end up with all of that in a fast step, right? So this is our fast and final step. We're gonna get CH3, C, H, and then there's a CH3 attached to that as well, right? And then we have COH, so that gets incorporated in. We have our CH3, another CH3 down here, as from before. And then we have CH2, CH2, CH3. And the side product is gonna be our NABR. So the Na that remained from this hydroxide, from this hydroxyl group. So we're gonna have Na, and then the Br that was kicked off from this step is gonna combine with it, and we get NABR, right? So this is how that mechanism works. It's a two-step process, nucleophilic substitution, and so that covers what's expected for this question here, okay? All right, so let's clear that and move on to the other part. So that was for 3 marks, that two-step mechanism, okay? All right, so part B says, we're moving on to a different kind of reaction now. So we are looking at benzenes and the conversion of benzene into nitrobenzene, right? So now they're asking us, how do we convert benzene into nitrobenzene? So in this particular case, I would just do like a quick sketch so I see what we're working with, what functional groups are changing and so on. So I'm gonna just sketch it up top up here. I'm gonna sketch my benzene, right? My benzene is gonna be this ring system that we have here, made up of these conjugated bonds, right? So that's my benzene. And what we want to do is we want to convert this into nitrobenzene. So there'll be a nitro group attached on it when all is said and done. So that's what we're trying to do. That's our goal, right? So here's my nitrobenzene. So there's a nitro group on top now, right? So in order to do this kind of conversion from benzene to nitrobenzene, you're asking us what reagent do we need, right? So essentially what we're doing is the nitration of benzene. We're nitrating benzene. And to do that, what we need is we need a mixture, or we call this mixture a nitrating mixture, and that's just comprised of concentrated HNO3 and concentrated H2SO4, right? So that's our nitrating mixture that we use to nitrate that benzene, and that will give us nitrobenzene. So these are the reagents that we need. And the conditions is that we need a fairly low temperature particularly for this nitrating mixture. So we're gonna have a low temperature And that temperature is going to be around 50 degrees C. So I'm going to write that temperature here. So we need to have a temperature of around 50 degrees Celsius for this reaction, okay? So that's this. So that's that, right? That's our answer. All right, so then now they're saying, outline the mechanism for the reaction described in B part 1 above. So we have to describe a mechanism for this reaction. So they're asking us to come up with a mechanism for the nitration of benzene. So how are we able to use these reagents and these conditions to go from here to here and to show that in a mechanism form, right? So I'm just going to clear everything. So I have ample room to write my mechanism because my mechanism in this particular case is worth 5 marks. So there's a lot of information that's needed, or fairly substantial amount of information that's needed. And so this particular mechanism, right, as it relates to the benzene ring, right, the mechanism by which these aromatic compounds are going to react is largely electrophilic substitution. In this case is what's going to happen. So we're going to have electrophilic substitution of the benzene ring, right, of benzene. And that's because largely the benzene ring is an electron-rich, right? It's a very electron-rich molecules. And so electrophiles, right, which are positively charged, are going to want to get attracted to it. And so that's really the basis of this mechanism. So let's just start by drawing our benzene ring again. That's our starting point, right? So here's my benzene ring. Here's my benzene ring, right? So this is my benzene ring. Again, conjugated bonds. So let me just show those conjugated bonds. So here's my benzene ring, right? And the reaction conditions or the reagents that we use were, let's write those again. So we are reacting, our nitrating mixture consists of HNO3, right? And sulfuric acid, and that's for a reason, because that's how we're gonna generate our new or electrophile that's gonna come in and attack this benzene ring, right? So this is how we generate that. So I think it's a good idea to just write this first step of this generation of the electrophile just for completeness, right? So what we're gonna do is we're gonna combine the nitric acid with the sulfuric acid, and we're gonna end up getting NO2 plus, right, plus 2HSO4 minus plus a hydroxonium ion, so that's H3O plus, right? And it should be a 2 here to balance it. And so what you see right away is that the key thing that we want to see that we got from mixing that from our nitrating mixture was this electrophile. So this is our electrophile, and this is what's going to do all the magic, all the substitution, right? So we have our electrophile as a result of from this nitrating mixture. All right, so let's go back to benzene now. So we have benzene here, and we have our electrophile NO2 plus. So let's just put that here, NO2 plus. And we said electrophiles are electron loving, right? And so what's going to happen is that one of these bonds are going to donate its 2 electrons to this electrophile, because electrophiles love electrons, right? And so this ring, one of these double bonds are going to donate 2 of its electrons to this nitrate. And so what's going to then happen, right, is that we're going to have a bond, right, being formed at this carbon here and between this carbon up here and the nitrate. So we show that by carrying an arrow over here. And let me just draw my benzene ring again. So that's my benzene ring. Well, let me be consistent with the conjugated bonds. So I'm going to show my conjugated bond that I have here and here. And then in this case, that bond was broken, right? So I only have one for this carbon here, and I have my NO2 plus attached to it. So that would go somewhere here, right? So that's my electrophile that's added on there. And then of course, I would have had a hydrogen that's attached to this carbon from before. So that's still there for now, right? And so effectively, what has happened is that this carbon ended up having a net positive charge, right? Because you can see that there are now only 1, 2, 3 bonds on it because there's the hydrogen there. So it's kind of deficient, right? So it has 1 bond to here, 1 to here, and 1 to here. So there are 3 bonds coming from this carbon, but we know that carbon needs to have 4 bonds because it's tetravalent, right? And the reason why it only ended up having 3 bonds left is because the double bond was converted to a single bond by virtue of it giving up 2 of its electrons to the NO2 plus, right? So now I have a positive charge here. And so what's going to happen then is the HSO4 that remains in the solution, right, is going to act as a weak base, and it's going to just kind of come and pull off this hydrogen, right? And this hydrogen will then donate its electrons from this bond back to that positive center, positive carbon. And so what's going to happen as a result of that is that we're going to end up getting this kind of substitution taking place, where now we have our benzene ring, right? And so because this hydrogen left, right, and donated its electron back to this carbon, we're going to recover our double bond that was there before. And then this one was here as well from before. And then now our nitrate group is still going to remain at the top there. So let me put that back in the electrophile color. So that will be NO2, right? So that's what we added on by substitution, or substituted out our hydrogen for. So then, of course, that hydrogen that was taken off by this weak base is going to just be here as well, right? So just to recap, we use this nitrating mixture, so the mixture of nitrous acid and sulfuric acid, to generate our electrophile. We have this HSO4 or weak base, or the conjugate base of this acid that gets formed as well. And then we have the H3O plus, so that's our hydroxonium ion, right? All right, so the first step now, after we've generated our electrophile here, the electrophile is electron loving, and so this electron rich area, benzene ring, is gonna be attracted to it, or it is going to be attracted to the electron rich area because it's an electrophile and they love electrons. And so what happens is that this bond, this double bond, is reduced to a single bond because one of the bonds are going to donate all of its electron to the NO2 plus. And so that's how this new bond gets formed up here, up top. And of course, we still have our hydrogen there. So what happens is that because the double bond went away and now we have a single bond, what happened at this particular carbon, so this second carbon, is that this carbon ended up only having 1, 2, 3 bonds, right? As opposed to the 4 bonds that it had here, right? Because that double bond went away. So this carbon now ends up having a net positive charge on it. And so in order to get rid of that positive charge, the weak base is going to take off this hydrogen and enables that hydrogen to then give up these 2 electrons to get rid of this positive charge. And so when that happens, we can get this double bond back and get rid of this positive charge. So we get our double bond back, and our NO2 is just added up here, and the H plus goes away. So that's how the electrophilic substitution of benzene works. And so the catalyst, or this H2SO4, gets regenerated using this H plus that we get. So what will happen is that the H plus, this one that gets substituted out for the NO2 plus, will then recombine with the HSO4, because remember, it's the HSO4 that pulled it off, right? So it's going to recombine, and we're going to get back our H2SO4 that we started with, right? So that should suffice for the mechanism for that reaction that was described up top, which is the nitration of benzene, okay? So that should suffice. So let's clear this now, and we'll move on to part C, right, which is a synthetic route from that nitrobenzene that we would have made in part B to compound E, which is shown in figure 1, right? So we're looking at this scheme now. We see that we're going from nitrobenzene, right, to phenyl. So we have a phenyl group now. So this is phenylamine. We have an amine group now. So we're going from nitrobenzene to phenylamine, and then we're forming what we call a diazonium salt, right? So that's what this is. And then we see that down here now, we have a phenol group, and that's attached to this group here that would have, you know, that this comes from the diazonium salt. So let's just kind of write what everything is here. So this is nitrobenzene, right? That we are generated from part B. This here is phenylamine, right? This here is our benzene diazonium chloride. So that's what we call that. It's a diazonium salt, right? It is polar. It has a chlorine and that N2 plus. And then finally, what we're going to get is compound E, right? So they're asking us now to figure out the reagents that were used for the first reaction, the second reaction, and the third reaction, right? So let us scroll up a bit. And then I'll just move these up as well. So let's move these back up. So they're right under their respective molecules. Right? So that's what we're working with. And so they're asking us now to come up with the reagents that would be used for the reactions 1, 2, and 3. So let's bring this up. All right. So again, for reaction 1, we're going from nitrobenzene to phenylamine, right? So in essence, what we're doing is we're reducing these 2 oxygens to hydrogens, right? And in order to do that, the reagents that we need are tin. So I'll just write the symbol of tin. So we're going to need tin and concentrated HCl to do that transition, right? So to reduce that nitrobenzene to phenylamine, we need tin and concentrated HCl. All right, so then for reaction 2 now, we're going from phenylamine to benzene diazonium chloride. And in order to do that transition, we need nitrous acid, right? So let me put nitrous acid here. We're going to need nitrous acid, which is HNO2. And the way that we generate nitrous acid is we do that by combining, we're going to combine to get the nitrous acid. We're going to combine, NaCN, so sodium cyanide, with HCl. And that's how we're going to get our HNO2, or nitrous acid, that is needed to convert the phenylamine into the benzene diazonium chloride, right? So then third and finally, they want us to say, how are we going to get from this benzene diazonium chloride to compound E? And if you look at compound E, you'd realize that we still have this structure, right? But now what we have is the addition of a phenol group to it, right? So this is a benzene ring with an OH on it. We call it a phenol. So we have a phenol group on it. And for that particular transition, right, what we're going to need is an alkaline solution of phenol, right? So let's just write that here. So we need an alkaline solution of phenol for that, right? So those are our reagents that we need. And so that should give us all 3 marks, okay? So we're good there. So let's scroll down. Let's clear this and then scroll down. So they're saying state the class of compounds to which E belongs, given the commercial significance of such compounds. So the family that this compound, right, belongs to is known as azodies or azo compounds. That's what we call it when we have this kind of reaction where we couple a phenol, right? We couple that phenol with our diazonium salt. So we react this diazonium salt with our alkaline phenol. It's called a coupling reaction, and the net result of that is this compound here that's called the azodie. So let's just write that down, that we produce azodies, right? And these can be used as, so azodies are compounds, and they can be used as indicators and we can use them in the textile or clothing, right? So that's another name for clothing, and the painting industry. So to create paints, we can use them, okay? So we can use them in those industries, and we do use them in those industries commercially. So it's an azodiol compound that we create. So that compound in step E, in part E, that compound E is an azodiol compound, can be used as indicators, and we can use them in the textile and painting industry. All right, so that is that. And now we are on to part D. So let's clear that. And then we're moving on to part D. Okay, so part D, for part D, they're asking us to consider the statement that all amines are weak bases and aqueous solution of amines are basic, right? So first of all, I guess we just have to refresh ourselves on what a base is, right? And a base, according to Bronsted-Lowry theory, right? So let me just write Bronsted-Lowry base. This is from our Unit 1 knowledge now. So a Bronsted-Lowry base is an acceptor of protons, right? Right? Or H plus, right? So that's a Bronsted-Lowry base. That's how we define a base, right? So if we're saying here, essentially, the statement is saying that amines are weak bases and aqueous solution of amines are basic, right? So that means that they're acceptors of protons, but on a very weak level. right? So they don't accept protons that well, but that's what they would do, right? If they're doing anything, they would be on the side of a base, a Bronsellary base, which is an acceptor of protons, right? So it's saying now use the compound ethylamine and a relevant equation to explain the statement above. So we're explaining how come we get amines to be weak bases. So this compound and an equation that we can come up with is essentially this equation here that shows how bases behave, right? So this is our formula for ethylamine. So it's CH3, CH2, NH2, right? And so as we mentioned above, so this is in aqueous solution. So as we mentioned above, according to Bronsellary theory, right, a base is an acceptor of protons. So we can show the ethylamine accepting a proton, right, in aqueous solution. And what that gives us then is an ammonium salt, right? Very similar, analogous to what would happen in the case of ammonia, right? So it's often likened to ammonia. So we have this ethylamine that's accepting a proton, and what we're going to get is this ammonium salt, right? NH3 plus aqueous, and of course water, right? So that's what we're gonna get. We get a salt and water. Because, and that's because, right, this ethylamine is acting as a weak base that's then reacting with the H plus ions, right, which these are acids, right? So an acid and a base coming together to form a salt and water. So this formula, or this equation rather, can explain the statement above that amines are weak bases because they do accept protons, right, to then form a salt, right? This ammonium salt and water. Okay, so that's how we would show that. And then for part 2 now, let us scroll up. So I'm just gonna clear that and then scroll up to part 2, which says that the pKb values of ethanamide, ethylamine, and phenylamine, right, are 14.51, 3.27, and 9.38 respectively. And they're saying account for the differences in these pKb values, right? So let us draw our structures that they're talking about and asking us to compare their pKb values first of all. Let's start there. So for ethanamide, right, the structure for ethanamide, I'm going to draw it here. Well, actually, let's do this first. Let us rank them from lowest pKa, lowest pKb to highest pKb, and then we can draw the structures in such a way, and then we'll account for the differences. So let's draw it from, what is the lowest one? The lowest one would be ethylamine. So let's put ethylamine here. And we're gonna draw the structure. And let's put, which one is the middle one? Let's put phenylamine in the middle. That's the medium pKb value. So let's put phenylamine structure in the middle. And then let's put ethanamide here. So again, I'm just ordering them in terms of from lowest pKb to highest pKb. So that's just how I'm ordering it, to draw them so we can see if there's a trend, if any at all, how we explain that, right? So we have ethylamine, and I'm going to draw that one here. They said that the pKb of that one is 3.27. That's the one that they gave us for ethylamine. And for phenylamine, they said it was 9.38, right? And then for what is this, ethanamide, they said it was 14.51. Right? So now I've arranged them from lowest pKb to highest pKb. So I'm going to draw the structure now, and then we'll discuss the differences that we see, okay? So for ethylamine, right, the structure, we spoke about that up top, and the structure for that one is just H, C, H, H, C, H, H, and then that's attached to the NH group, right? So that amine is there. So this is ethyl, the ethyl portion, and this is the amine group. And for phenylamine, of course, we know we're gonna have our phenyl ring. So just this ring here, right? We're gonna have our phenyl ring, and then of course our amine group is attached up top, right? And then for ethanamide, the structure is gonna have only 2 carbons, right? So it's gonna be CH3, C double bond O, and then we have the NH. So that is how we write the formula of ethanamide. So we have our ethanamide structure, we have our phenylamine structure, and our ethylamine structure. Okay, so now let's look at the structures and see what's going on and how that might affect, you know, these pKb values. So to do that, let's just do a quick recap on what pKb values actually tell us. So let's talk about that real quick, right? So I'm just going to jot that here, right? So the pKb is essentially the negative log to the base 10 of the Kb value of a base, right? And the Kb value, right, tells us how strong or how weak of a base we have. It's the base dissociation constant, right? Base dissociation constant is what the Kb is, right? So it tells us how strong or weak our base is. If we have a high Kb, right, this pKb is going to be low, and a high Kb, so let's write that here. A high Kb is associated with a strong base. A high Kb is associated with a strong base, a base that's dissociating to a great extent in aqueous solutions. And then a low Kb, right, would mean that we have a weak base, one that's not dissociating as much in aqueous solutions, right? And so based on this relationship between pKb and Kb, we know that if we have a high Kb here and we take the log of it, we're going to get a very tiny pKb. So a high Kb corresponds to a low pKb. And so that means that our strong base, or our strongest base, would have a low pKb, right? Now, if we have a low Kb, which is associated with a weak base, right? And we take the log, the negative log to the base 10 of that tiny, tiny Kb, a low Kb, we're going to get a large pKb, because that's how the logarithm function work, right? So I would end up getting, in this case, a high, right, pKb. So what you will find then, right, if we're looking at this thing holistically now, strong bases have a low pKb, weak bases have a high pKb. So when we look up here now where we did this ranking, right, we see that ethanamide had the highest pKb and ethylamine had the lowest pKb. So that means that this would be the strongest base, right? And this would be the weakest one, right? So this is our strongest, and this is just intermediate. Phenylamine is intermediate, it's just in the middle, right? It's just smacked in between both of those. So what we're gonna do now is we're gonna look at the structure of these molecules and think to ourselves, why might it be that this is the strongest base and this is the intermediate one and this is the weakest one, right? And so what we have to think about is back to our original definition of a base, right? We said that a base is a what? Is an acceptor of protons, right? So a base is an acceptor of protons. It means that if you have a proton that has a positive charge, right, and you have a region on a molecule that has a negative charge associated with it, right? And the stronger that negative charge is the greater the attraction is going to be for a proton. And so that will give us a stronger base, right? If we have a stronger attraction between negative parts of our molecule and this H+ ion, then we will have a strong base because it will readily want to accept that proton, which is what bases do, right? According to Bronsted-Lowry theory, right? And so here we are now. Let's look at the structure of ethylamine, right? So attached to this nitrogen here, which is the negative center because it has that lone pair, right? So let's just write that on all of them. The nitrogen is the key functionality here because that has the lone pairs, right? So that's that. And then of course this one would have a lone pair as well, right? Because that's how nitrogen bonds. All right. So attached to this nitrogen, we have an ethyl group. There are 2 carbons here, so this is an ethyl group. And ethyl groups or alkyl groups in general are electron donating groups, right? So ethyl group is a donating group, electron donating group. All right. So what that's gonna do, right, is it's gonna donate all of its electrons towards the nitrogen. And when that donation happens, right, what's gonna happen is that you're gonna have a very negative nitrogen. So the nitrogen will be highly negative. So highly negative nitrogen atom, right? And as a result of that, as we said, if it's highly negative, it's gonna very strongly attract our proton, and that's what we call bases. A strong base is one that strongly attracts or accepts another proton. And so that's what's gonna happen here when we have this electron donating ethyl group attached to it, right? So this ethyl group is what causes that strong electron donating effect, gives its electrons to its electron density, right, is projected onto this nitrogen. And so the nitrogen is going to accept a proton very, very strongly because of that strong nitrogen, that strong negative charge that's on the nitrogen, right? So it's going to be a highly negative N atom, and that's going to accept H+ ions very strongly. Now, the phenyl ring, right? The phenyl ring is what we call electron withdrawing. So the phenyl ring is going to withdraw electrons from this nitrogen. And the net effect is that this is going to be less electron rich and more on the positive side of things. And so we know that positive and positive is not going to work, right? So the H+ is already positive. We don't need our nitrogen to be positive as well because that's not going to work. It's going to be like some repulsion, right? So it's not going to accept readily as this would. It's not going to readily accept a proton, and that's what we define bases as. So if you can't readily do that as much as this one would be able to do it, then it's going to be a weaker base when compared to our ethyl group bearing amine, right? So this is a weaker base on account of the fact that the phenyl ring, so let's write that, phenyl ring is electron withdrawing, and so it pulls all the negative charges to itself, right? So the phenyl ring is electron withdrawing, and that's what results in this being a weaker base because it pulls all the charges to itself, resulting in a more positive nitrogen. And if it's positive, it's not going to be able to accept protons as well as the ethylamine was able to, right? And so when we come over here now to our ethanamide, what we see is that we have a carbonyl group that's attached to it, right? And we know that these carbonyl groups are also electron withdrawing because they have what you have your partial negative charge here on the carbonyl and a partial positive. So it's gonna, the net effect is that it's gonna pull electrons to itself, and it's gonna do so much more strongly than a phenyl ring does, right? So let's write that down as well. That's our carbonyl group, right? Carbonyl group that is attached to the nitrogen, right, is electron withdrawing, right? So it pulls those negative charges to itself. It's gonna make our nitrogen positive, right? More positive than it would have been ordinarily. or as in compared to the case of ethylamine. And so it's going to make this nitrogen more positive, right? And so that's not going to be able to attract, again, a proton as well, right? It's going to be able to do so to even a lesser extent than this, because these are more electron withdrawing. So it pulls all the negative charges off of this, makes it more positive, and it's going to be harder for a base to want to come on in, right? Because the base, it's going to make a hydrogen, the H plus not want to go there because it's positive there. And that what's attractive to the H plus is a more negative nitrogen, okay? So that's how we kind of explain these differences in pKb value. It's related to the structure of these different compounds and the fact that in the one case for ethylamine, we have donating groups attached to the nitrogen, so it makes it more negative or electron rich, and then it can attract a H plus ion, and that's what good bases do. In this case, we have a withdrawing group, which is the phenyl ring. And in this case, we also have a withdrawing group attached to the nitrogen, but in this case, it is far more withdrawing than this one. And so what we see is that when this one withdraws all the electrons, this is going to be more positive than in the case of the phenylamine. And so we see that this one is lesser able to act as a base than the phenylamine. And so that's how these pKb values reflect that. Remember now, low pKb, strong base. High pKb, weak base. So that's how we're able to rank them that way, okay? Definitely give me any comments if you have any questions or any clarifying question on that. So we're gonna just stop, so clear this now, and then move on to the next question, which is our reactions of phenols, right? So let's just fill out this table with some of the reactions of phenols. And so we're going to complete the table by inserting in the appropriate observations and reagents, right? So we have our phenol here. So again, this is our aromatic alcohol, essentially is what the phenol is, right? And so the kind of reactions that it can participate in are those that are related to the aromatics, or to the benzene ring, as well as the functional group that is OH up here, right? And so in the first case, what we're seeing is that there's a transition or a conversion of this phenol into this salt, right? So this is like a salt or a phenolic salt, a salt of the phenol where Na is attached, right? And so in terms of reagents that we would need to go from here to here, we would need aqueous NaOH, right? Because that's where our Na is going to come from. So we need aqueous NaOH. And what we're going to get is a soluble salt out of that. So we'll just see that whatever our product is going to be soluble in that aqueous solution. And remember that the phenol itself is not very soluble in aqueous solutions. And so what we'll see is then maybe a reduction from a cloudy kind of mixture to a clearer mixture, right? Because our salt that's then formed as a result of the NaOH reacting with the phenol is going to be a soluble salt, right? So this is a soluble salt. You see that it's polar, it has its minus and its plus. So it's going to be soluble in aqueous solution. And so we'll see that maybe our reaction mixture would go from cloudy to a clear mixture, right? Or a clearer mixture on account of the soluble salt that's being formed, okay? So again, our reagent is NaOH. And when we add the NaOH to this, we are going to get our salt, right, of that phenol. All right. So for the second step, what we're looking at is the transition or the conversion of phenol into, let's scroll up and clear that so we have more space. So what we're looking at is the conversion of phenol into what is this? This is 2,4,6 tribromo phenol. So let's just write down that name so we see what we have. So we have 2, 4, 6, right? Tribromo phenol, right? And so in order for this conversion to take place, we're gonna need bromine solution. So we need Br2 aqueous. So we're gonna need a bromine solution. And of course, that's going to be electrophilically substituted onto our ring. And so it goes to the 2, 4, and 6 position because this OH group is 2, 4, 6 directing, right? That's what it does with the benzene, with the bromine, right? So it's going to direct it to the 2nd carbon, the 4th carbon, and the 6th carbon. So that's how we get 2, 4, 6 tribromophenol, right? And so we need the Br2 aqueous to do that. And what we're going to see is that we're going to get a fluffy white precipitate. And that precipitate is this, right? This tribromophenol is a fluffy white precipitate. So that's what we're going to see as one of our observations. We're also going to see that the bromine solution is decolorized, right? So decolorized bromine solution, right? And so remember, bromine solution is normally brown. What we're going to see is that we're going to go from brown to colorless, right? So those are 2 observations that we would see in that case. And a third one might be that we'll see fumes of HBr, because this is a very vigorous reaction, right, in which we're substituting out a hydrogen here, 1 here, and 1 here. So we're going to get HBr as a side product as well. And it's going to be fumes because it's a very rapid reaction, okay? All right, so let's look at part 4 now, part 5 now, right? So let's clear and move down. So part 5 now, that represents the reagents that we need for the transition from phenol to what we see here is an ester, right? So let's just zero in and look at this. So this is our ester linkage that's here, right? So you see that this is a carbonyl group, and then we have a O that's coming from the phenol, and then we have just the regular straight chain portion of whatever we use to make this ester, which we're going to talk about now, right? So we have our phenol, right? And there's a reaction that phenols do with acyl halides to create esters, right? So it's going to react with an acyl halide to create this ester. So this is an ester, right? And in particular, this is which ester? There are like 2 carbons here, right? So that would be from a acyl chloride, right? So that's what that is coming from. And then here we have our phenyl ring. And so this would be, if we're supposed to give it a name, the first part comes from the alcohol, right? So it would be a phenyl. And then because we have 2 carbons here, 1 here, and then now another 1 here, right? That has the 3 hydrogens attached to it, right? So the first part of our ester name comes from the phenol. So it would be phenyl, and then 1, 2, there are 2 carbons here. So it would be phenyl ethanoate. So that would be our ester that's formed, right? And so the way that we form esters from phenol is that we need an acyl halide. And in this particular case, because we saw that this group was an ethyl group, right? That's why we got ethanoate. We can say that we would need an ethanol halide, right? So a halide could be a chloride. So we would use ethanol chloride, right? And that acts as kind of like an acid. It has acidic character. And so you might remember from earlier on that alcohols and acids react to produce esters. And so this is essentially acting as an acid, right? The ethanol chloride. And so the structure of that would be, of course, if we look at this, we can just kind of see that it would be CH, and then of course, this is attached to the carbonyl carbon that we see in that ester linkage here. And then, of course, our halide X would be here. And we can just say, for argument's sake, that halide is chlorine, right? So ethanol chloride would look like this. So let me just draw it up here. It would be C double bond O Cl, right? And then that's attached to the methyl. So when we look at this, we can see that we have 2 carbons, right? So that's ethanoyl chloride. So that's what this is. And if we react ethanoyl chloride with phenols, we're going to get an ester, a phenyl ester. So this one in particular would be phenyl ethanoate. Okay? And that's it, guys. So let's talk about, let's see, let's talk about what we would observe. For this question, we don't necessarily need to put it, but let's see what we would observe. Because we're using an ethanoyl chloride, right? What we would have is that, you know, there's the chlorine, right, goes away. And so we would see fumes of HCl coming off of that. And again, there's like a fairly rapid reaction that takes place between the phenol and the ethanoyl chloride. So that's why we would see fumes of HCl coming off as that ester is formed. So this HCl gets condensed off as that ester is made. And we might smell some sweet smelling smells, right? Because it is an ester, and esters are sweet smelling, right? They have a pleasant aroma for us. So we might get a sweet smell or a pleasant aroma because it's an ester that's being formed, right? So those are things that we might observe. And so that's it for this question. If you have any questions, feel free to send me a comment and just let me know. Let me know if this all made sense for you, okay? All right.